This lecture we will be covering the accelerated flights. It is chapter number 6 in Anderson's book. Here, the basic concepts that we have studied in chapter number 5, steady flight, apply with a bit of a twist. As the aircraft is unsteady, which means it is accelerating, we are going to cover turns. So we deal with the situations other than steady flight. This includes level turns, pull up and pull down maneuvers, load factor limits, VN diagram, energy concept, and takeoff and landing performance. The first part covers the level turn. The altitude of the aircraft does not change. The aircraft is at a bank angle as shown. This is from the front, all right? So as you see from the front, the aircraft is at a bank angle phi. This causes the lift vector to be towards the center of your circle. A component of the lift vector is in this direction. This component, as the L sine phi, forces the aircraft towards the center. Whereas the L cos phi, this is cosine part. The cos part basically overcomes the weight. The turning radius is defined as r, the bank angle is phi, and the turn angle is psi. So the weight is balanced by L cos phi, right? So this is L cos phi. This covers the weight, whereas the L sine phi, which is in this direction, provides the necessary force to turn the aircraft in a radius r. There are two important factors whenever we are considering the turning. One is the turning radius and the other is the turning rate. So how do we go about it? First thing, how do we define cos phi? So as L cos phi is equal to W, this gives us cos of phi is equal to W over L, or 1 over lift over weight. We define the term N as the ratio of the lift force to the weight. Now for steady flight, N was always equal to 1. Here, as a part of the lift vector is towards the center of the circle, the lift vector overall is greater than the weight. So cos phi is 1 over N, or phi is cos inverse of 1 over N. On the other side, we have the centrifugal force, mv theta square over r, which is equal to L sine theta. As we take a look at it, we isolate radius from it, and we get r is equal to mv square over L sine theta is equal to weight over lift into v square over g sine theta, as m is equal to weight divided by gravity. M is equal to w over g. So the radius equation comes out to be v square over g n sine theta. Now this n is a very useful term. This is defined as the load factor. This is the load on the wings of the aircraft. As a matter of fact, your aircraft is actually pulling up that many weights. So if load factor is 2 or n is 2, your wings are actually lifting up twice the weight of the aircraft. If the load factor is 3, your wings are lifting up 3 times the weight of the aircraft. So n is very important. Now we know the basic geometric equation of cos square phi plus sine square phi is equal to 1. We replace cos square phi with 1 over n, and we get an equation in terms of sine phi. We put that equation in the equation for radius of turn r, and we get the equation for r in terms of n. Now we know that the rate of turn is how the angle psi changes with time, and that is v infinity over r. So that gives us an omega in terms of g times and root n square minus 1 divided by v infinity. Now we are going to define these in terms of the CL and CD. The drag obviously is half rho v square s times CD naught plus KCL square. This is something that you have done many times. Lift used to be this, but now it is multiplied by an n value as well. All right. So lift is n times the weight, or CL is 2nw over rho infinity v infinity square times s. We are going to put this CL value in the equation above for CD, and we get the value of thrust, which is equal to drag, of course. Thrust will always be equal to drag. So thrust is equal to half rho v square s times CD naught plus k times 2nw over rho v infinity square s square. All right. And this gives us the value of n as given in this equation here. All right. Now if we replace thrust with T max, we get the value of n max. All right. This is the maximum G's this aircraft can pull. This is the maximum load factor that the aircraft can pull. Now this is the aerodynamic loading. All right. This is not bound by the structural limitation here. So structural limitation usually comes in before the aerodynamic loading for most of the aircraft. For example, if you are pulling in 8 Gs in an aircraft that is not designed to lift 8 Gs or 4 Gs or 5 Gs, the wings will break. All right. Why? Because the wings can only lift a certain amount of weight. All right. So n max is this equation. However, this equation is only aerodynamic. So if we plot the value of n, we get a curve, right? This curve over here, all the way here, and it goes the red line. So n max for all cases is equal to lift over drag into thrust over weight max. All right. It is without max for all of this area under it, and for all of the cases this is L over D into T over W max. Now if we know that L over D max occurs at a certain point, that point here is B. All right. This was the dip in your drag curve. So if you are at the dip in your drag curve, you get the maximum of maximum. All right. So you get the maximum n possible. That is when you're flying at your L over D max, which was the dip in your drag curve. And at that point, if you have the throttle at maximum, you can theoretically achieve the maximum load factor. Okay. However, like we studied before, much before that point reaches, your aircraft will stall. Okay. So in that case, the maximum G's that you can pull is half rho v square CL max divided by wing loading. And that is your this curve here. All right. So this is against the velocity. If we put in CL max over different velocity settings, we will get the n max. All right. So the aircraft will stall. This line means the aircraft will stall. However, this line is possible over here. So if you're flying really, really slow and you want to pull up really fast, your aircraft will stall. That is the stall limit. And we already know that cos phi is equal to 1 over n. So cos phi max, which is the maximum turn radius, turn angle, or the bank angle, is given by 1 over n max, right? And for most of the cases, it should not exceed 90 degrees anyways, but for most of the cases, it's about 80 degrees, right? So the angle which is indicated towards the right-hand side is shown here, okay? Whereas the maximum load factor that the aircraft can achieve is shown on the left-hand side of the plot. Beyond this point, thrust is the limiting factor. This side, thrust is the limiting factor, whereas on the left-hand side, stall is the limiting factor. This also gives us a new Vstall, and that new Vstall is 2 over rho W over S N over CL max. In original case, in the steady flight case, n was equal to 1. So it's the same equation, but here instead of 2w or rho as CL max, we have 2wn over CL max, obviously because we are lifting n times the weight. Now, important thing to measure is the minimum turning radius. So we take the equation for R and we differentiate it, right? And we differentiate it in terms of Q infinity, which is your dynamic pressure. Why? Because it's easier that way. And we solve this equation, we set the differential equal to 0, we solve it. I haven't done the steps over here, but ultimately you get a V infinity for minimum radius as 2k times W over S divided by rho infinity T over W under root. That gives us the minimum radius load factor as 2 minus 4k CD naught over T over W square. And putting this n in our equation gives us the radius minimum. The minimum turning radius is 4k times wing loading divided by g times rho infinity T over W under root 1 minus 4k CD naught thrust to weight ratio square. The next thing is the maximum turning speed or maximum turning rate. Here we have the equation omega is equal to g times n square minus 1 over V infinity. The same thing we do as we did in the previous one. We differentiate it in terms of V infinity and set it to equal to 0. This gives us the velocity for fastest turning radius as 2 times wing loading divided by rho infinity raised to power 1/2 times k over CD naught raised to power 1/4. The maximum load factor N for maximum turn radius is thrust to weight ratio divided by 4k divided by k CD naught under root minus 1 raised to power 1/2, and the maximum turn rate as this. The next part deals with pull up and pull down maneuvers. In this particular case, the aircraft is changing its attitude. All right. However, in current situation, we are assuming that the altitude is not changing, which means the height of the aircraft is not changing, right? The angle of maneuver is theta, and for simplicity, we consider both bank angle phi and the thrust angle psi as 0. Epsilon is 0, all right? We have always considered epsilon equal to 0, which means that our engines are in the same line as our thrust vector or aircraft vector, okay? So thrust vector and the aircraft direction are same. And here we are assuming that the aircraft is not pulling up while turning or pulling down while turning. So turn is 0 here. So the upward force towards the center of the circle, all right, the force that is towards this direction is the force that causes the aircraft to go up or go down. All right, so pull up or pull down. And that will be equal to the difference between the lift vector and the component of weight which is in the direction of this line. All right, so component of weight which is in direction of the lift vector. So the difference of those two is going to be mv infinity square over r. Okay, again radius is r here, or mv infinity square r is equal to L minus W if we assume that it is just the start of pull-up maneuver, okay, which is where you have the hardest G's while you're pulling up, and then again pulling down is the second one, but pulling up is the hardest G's that you pull. So radius r is given by v square over g times n minus 1, and the rate of turn, which is v infinity over r, will give us omega is equal to g times n minus 1 over v infinity. Right. Now the other case is your aircraft is at a height and it is upside down, and now you're doing a pull down maneuver. So the start of pull down maneuver, your mv square over r will be both these forces, lift and weight. So R will be given as V infinity squared divided by G times n plus 1, and omega will be G times n plus 1 over V infinity. Now we are going to talk about the load factor, right? So in level, we have the equation for radius for level turn, pull up and pull down on the left hand side, these three equations. We are going to assume that the load factor is very, very high, which means n is much higher than 1. This means that we can ignore the -1 or +1. All right, so R is equal to V squared over Gn. The minimum radius is 2 over rho G CL max times weight wing loading. On the other hand, if we are doing the rate of turn, these are the equations for omega. If we assume that for a large load factor, again n is greater than, much greater than 1, then the turning rate is Gn over V infinity. The fastest turning rate is going to be G times under root rho infinity CL max and max over 2 times omega, 2 times wing loading. This basically means that you're turning so hard that you're stalling the aircraft. Okay, N max will be half rho V infinity square CL max over wing loading. So this is the crux of your turns, where you're turning up or down, or as previously we did, we're turning the aircraft in a circle. In the next lecture, we are going to cover the limit load factors, right? How the structure comes into play, where you cannot turn beyond a certain load factor, all right? And what will be the rate for that?